All right. So hello, everybody. It's a great pleasure today to have Barak Kol talk to us. I think most of us, if not all, know him already. Uh, um, um, Barak is, of course, from the Hebrew University, and he will tell us today about flux-based statistical theory of the three-body system. So please, Barak.
Thank you, Shahar. And I would like to thank you for organizing this Israeli gravity seminar and for the leadership in this project. It's I think it's a very welcome project also to socially put people together. And today this time I will tell you about work which is in gravity, but not in GR, at least not directly. So there will be some geometrical ideas. Yes? Okay, someone was not muted, but okay. So I will tell you about the Newtonian three-body system and some recent advances on the problem. The work is it's based on work that I did in the last 4 years, and I listed here 4 papers, 5 papers, the 5th of which is accepted for publication, and the rest were already published. And out of the collaborators that you can see their names here, I will mention Yogesh, who is here with us and is on a postdoc position in Bar Ilan University with Ofek. So mostly we will discuss 2 papers, the dynamical reduction and the flux-based. And there are 2 papers that describe numerical or simulation evidence from simulations, so they will be mentioned also. And this paper will not be mentioned. Okay, and please feel free to ask questions as always. So I thanked Shahar, and I'm going to tell you 2 things basically. One is how to formulate this problem, an improvement to the formulation. So I will call it dynamical reduction. I think we'll see in a moment why. And the other thing is how to find a solution, a dynamical solution, or how to reduce, more precisely, how to reduce the work that is required for a dynamical solution. And at the end, we'll also discuss evidence from simulations and the summary. So quickly, the problem. 3-body problem is, of course, 3-point particles, Newtonian. We have initial positions and velocities. We have between any pair the Newtonian gravitational force. And given initial conditions, the goal is to predict the motion. It is very easy to define this problem. That's it. That's the definition. But it's not easy to solve. We distinguish 2 cases. The non-hierarchical case, which will be the one that we discuss here, comparable masses and comparable separations. Okay, unlike, for instance, the system of the moon. The moon, Earth, Sun is hierarchical because the moon is much closer to the Earth than the Earth and the moon are close to the Sun. So this one is non-hierarchical. We'll focus on that, and that's the more difficult problem, as we will see. So this system has a lot of fascinating history, and it generated beautiful science. So I write here that it's rich, fruitful, and deep problem. It started with Newton over 330 years ago, and it's closely related to the following 4 branches of science: perturbation theory, the symplectic structure of mechanics, which is a dignified way of saying Poisson brackets, chaos, and topology. All of these really started from the 3-body problem but today I will not focus on the history, just to give us some flavor of the background. And we start immediately with the dynamical reduction. And the figure that we see here, somehow the three-body system will be represented by a point moving in this joint of three pipes. Okay, so this is where we're heading right now. So let's see. So we're going to simplify the dynamics through a choice of fewer variables. And in that sense, it's a reduction, fewer variables. And this is possible thanks to the availability of conserved quantities. So we'll have roughly 3-4 steps. Let's start with the first step, okay? So we have 3 coordinates, R1, R2, and R3. So altogether, we have 3 vector degrees of freedom, or 9 degrees of freedom. But there is one vector constraint in the center of mass, or due to the conservation of linear momentum, we have this constraint. And now there is a question of how do we choose? We know that we can choose 6 degrees of freedom. We can get rid of 3 degrees of freedom thanks to this conservation law. But is there a natural way to do it? How do we choose these 6 variables? For instance, in the two-body system, we know how to do it. There we define R equals R1 minus R2. How can we do it in the three-body problem? Well, here we have 3 ways of defining relative positions. R1, 2, namely R1 minus R2, R2, 3, and R3, 1. However, these are 9 quantities, and they are dependent. They satisfy a relation, relation, telling us that they sum up, that the sides of the triangle sum up to 0. So this would not, so this doesn't solve. Let's look at 2 familiar choices, 2 popular choices, which, however, are not symmetrical. And we will try to define a symmetrical one. So in the planetary case, where we have 2 light objects, call them planets, M1 and M2, and one heavy object, call it the sun, M3, then we simply take R12 and R13 to be our coordinates. These are known as the planetary ones. So we don't take R2, there's a mistake here, it should be R13 and R23. Yeah, and we don't take R12. So, this is one possibility. The other possibility is what may be called lunar coordinates, and they're known as Jacobi coordinates, Jacobi. We take R12 to be close, and then we keep them as one coordinate. And the center of mass of the binary system, we take its distance to 3. So that's the center of mass of 1 and 2 minus R3. And in this way, we choose 2 out of 3. But again, this assumes here a hierarchy of scale. In the previous case, a hierarchy of masses. And it would not be justified in a general case. So how can we do that in a non-hierarchical symmetrical case? So we get inspired by Lagrange's solution to the cubic. So this is now not a 3-body problem, but just a cubic polynomial. How does one solve that? Well, this is the beginning of group theory, actually, and famously Abel and Évariste Galois solved it in the early 19th century, but actually they both relied on Lagrange, who did it in 1771. He did the basic idea. showing why the cubic and the quartic can be solved, while the quintic and higher, the general polynomial equations of degree 5 or higher cannot be solved by a closed formula involving only various roots. And the way Lagrange proceeded is he considered if x's are the roots, he denoted by S0 the sum of them. That's easily found in terms of the coefficients of the equation, minus b over a. But then he also considered these combinations, where eta is the cubic root of unity. So he considered this S1 and S2, and then he observes that S1 cube and S2 cube are roots of an associated quadratic equation. And the coefficients of these quadratic equations are functions of these coefficients. So he can write the quadratic equation, he can solve for S1 cube and S2 cube, and then he takes the cubic root and he arrives at S1 and S2, and once he has all the three S's, he can, by linear transformation, find the roots, the X's. So the important point is this transformation, S1 and S2 being equal to this. They are called Lagrange resolvents. And now we're going to do something similar for the three-body problem, and we're going to define the following quantity. We're going to define complex relative position. So in the two-body case, it was R1 minus R2. Here we define this W, which this time is going to be complex, to be R1 plus eta R2 plus eta bar R3, where eta is again a cubic root of unity, but we call here the imaginary unit J, not I. This is not because I decided to become an electrical engineer, but because I will use I later. Okay, so I will have both I and J in a moment. This quantity, just like R1 minus R2, is translation invariant. So if you shift the system, W doesn't change. And that's exactly what you expect once you've factored out the center of mass. Moreover, it transforms nicely under permutations. So it cannot be completely invariant to permutations, but it transforms nicely. If you do a cyclic permutation, it's just a multiplication by eta. If you exchange 2 and 3, it's complex conjugation. And in this way, we go from 6 degrees of freedom to 6, because W is a complex vector. So it has 6 degrees of freedom. And they claim that this is a natural choice, just like R1 minus R2. Okay, so this is a new definition. It's not a new result, but it should be useful for any case of the three-body problem, not necessarily Newtonian even. When we factor out the center of mass. Next step is to take into account the conservation of angular momentum. So far, we took into account the conservation of linear momentum. For a moment, let us imagine that we're in a planar problem. So all three bodies are moving in the plane, and the angular momentum is just normal to this plane and conserved. Of course, being normal to this plane means that, well, the angular momentum is conjugate to rotations in the plane. So what we really want to factor out is rotations within the plane. And there is a nice way to think of rotations in the plane as a multiplication by a phase. We know that in the complex plane, multiplying by a phase is just like rotations. And here also, because we want to take into account the conservation of angular momentum, it's just like taking into account rotations. And we'll do that by using complex numbers. However, we already used complex numbers when we introduced this cubic root of unity. So in order to go around this, we introduce another imaginary root that this time we call I. So we have now two imaginary roots, both of them square to -1. And we simply take our complex vector and transform it into the x part of the vector. Now we are in the plane, becomes the real part, and it's still and the y part of the vector becomes the I imaginary part. So altogether now we have 4 quantities. It's a bicomplex number. It looks like W1 plus I times W2 plus J times W3 plus IJ times W4. Okay, so we have now 2 imaginary units, J and I. J is related to permutations, as we saw, and I is related to rotations of the plane. Both of them square to -1. I see it should be here -1. Okay, great, I will fix that. And they are independent and commuting. So it may sound to you like I'm reinventing the quaternions, but the quaternions are anti-commuting, these are commuting, and these are also known. They're known as bicomplex. So unlike the quaternions, you cannot always divide by them, but you can always multiply and you can always add them. Okay, so now if we're in the plane, the system is described by a single bicomplex W, which is really 4 degrees of freedom. Now we want to factor out the rotations or the dependence on the phase. And now we use something that we learned elsewhere. We learned in quantum mechanics that if we have a spinner is a pair of complex numbers. So a bicomplex number, it has 4 components, can also be thought as a pair of complex numbers. The ones without the J is complex, and the ones with the J is another complex number. So if we have a spinner, we know that we can get observables, or observables which are independent of a phase, by using the Pauli matrices. Okay, so let's use this idea of Pauli matrices to define quantities which are independent of rotation, namely depend only on the triangle geometry. So the 3 masses are always in a plane, and they have some triangle geometry, and we will define quantities which depend only on the geometry and not on rotation. And we can define it as follows. We take the W and divide it into W1 and W2, which are both I-complex numbers, one of them with J and the other without J. And then we define these quadratics Q by taking some kind of expectation value with Pauli-like matrices. So this should remind you the average spin vector of a spinner, right? So you put here the Pauli matrices, and if this were psi1 and psi2, you would get, and psi1 bar and psi2 star, you would get, oops. Okay, sorry. We would get the average spinner. So here we get these Qs, and these Qs are a little different than the Pauli matrices. We have the unit matrix, we have this matrix, which is like sigma 3, we have tau 4, which is like sigma 2, and instead of sigma x, we have 2 taus, tau 2 and tau 3. However, these Qs satisfy a relation Q1 plus Q2 plus Q3 equals to 0. So that means that really it's just a 3-dimensional space. And it also satisfies this relation. So this is inspired by Pauli matrices, as I explained, but you can also analyze the isotropic oscillator in the same way. And the isotropic oscillator is a particle moving in the plane under a restoring spring, which has the same spring constant in both directions. And there, when you go to the variables A and A dagger, then you can describe it by a bispinner, and you can use these Pauli matrices. They're called Stokes variables. So there are very much analogous stories. There is also the original Stokes story in optics, in polarizations. In mathematics, it's known as Hopf. And later in solid state physics, it became known as Bloch. Bloch sphere. So we have the Bloch sphere, the Poincare sphere. Never mind. It's all essentially the same. And here it's geometry space. So let's see. Here is just geometry space.
Barak?
Here is how it looks like. Yes, please.
Just a quick question about these two relations that you had in the previous slide.
Yes.
Did you explain where do they physically come from?
If
it's a simple, I mean, origin.
Can I add more insight into
Yeah.
this? Well, the second relation is the analog of the fact that if you take for a spinner and you compute S1 average, S2 average, and S3 average, then you get that S1 squared plus S2 squared plus S3 squared equals a constant. The magnitude of the average spinner is constant, independent of the spinner.
Right.
This one is the analog here, and here I'm not sure if I can give insight, but I can show you that tau 1 plus tau 2 plus tau 3, these three matrices, they sum to 0. So it's not independent.
I can see. Yeah.
Might be a factor half missing, but they don't actually sum to 0.
Oh,
right.
Thank you. Yes, I think there's a factor of half missing in tau 2 and tau 3. Thank you. Let's see. Yes, here I have it by chance written next to me. So yes, so there's a factor of half in tau 2 and tau 3, which is missing. Okay, and then you can at least see that from the definition, it follows, this identity follows. So unlike the Pauli matrices, which are 4 matrices which are independent, here we have 5 matrices, 5 2x2 matrices. They cannot be independent linearly. And indeed, tau 1 plus tau 2 plus tau 3 equals to 0. But I count all of them in order to preserve the permutation symmetry. So if I had thrown one of them away, I could have done that, but that would mean that I prefer 1 over 2 or over 3. Okay.
So now with the factor half restored, it looks like the summing to 0 is just a sum of the square roots of unity, summing up to 0. Right? You have basically plus and minus e to the I pi 2/3 pi I and stuff like that. It looks very similar.
You mean the sum of the 3 taus looks very much like the sum of the 3 cubic roots of unity, which sum to 0. I agree. Yes. Okay, good. So now let's look at this geometry space. So now, finally, we have these 5 Qs, but actually because of the 2 relations, there are only 3 of them. So it's a 3-dimensional space. So every point in this space gives us a shape of the triangle. Okay, so we look at the shape of triangle or the geometry of a triangle as a point in a 3-dimensional space. First of all, the radial coordinate in this Q space corresponds to the size of the triangle. So this is easy. So let's now focus on the unit sphere in this space. That corresponds to the shape of the triangle. It's also known as shape sphere. Okay, here it's written shape sphere. there are three special points on it where the triangles degenerate when 2 points meet. For instance, here points 1 and 2 meet. So it's a triangle where 1 and 2 are the same point and point 3 is somewhere else. So it's a very degenerate triangle. Actually, the whole equator is degenerate in the sense that it's collinear. So if 3 points are collinear, they are on the equator. The top point is an equilateral triangle, שווה צלעות, but right-handed, and the bottom pole is a left-handed equilateral triangle. So it's a nice way of mapping the shape of a triangle to a two-dimensional space. There's another much more familiar way. If we just record the three angles of the triangle, then we have three numbers which are constrained to sum to 180. So it's really only two numbers. So this is a way of also describing the shape of a triangle by a two-dimensional space. It's called the two-simplex. But here, this parameterization is smooth for going through collinearity. So, so it has some advantage. Altogether, oh, that's a shame. Just a minute. I want to show you now the geometry space. And there's a problem here. Let's see if I can I show it here? Yes. So let's see if I can share screen here. Can you allow my other person to share the tablet, Shahar?
Yeah, of course. Okay.
And I think I will need to unshare here. And thank you.
Okay.
Aha. Amazing. It works, right? Okay, so the picture now is that the three-dimensional space, a point in the three-dimensional space describes the shape of the triangle. And when you draw the equal energy surface, it looks like these three pipes connected. So the motion of the all three objects can be described by a single point. The planar motion can be described by a single point moving inside this joint pipe. So it's some kind of plumbing. And this is because of energy conservation. You cannot move outside of the surface of energy. And the three pipes correspond to the case where two are close by and the third one is far away. And because you have three possible ways of choosing a binary out of three bodies, that's why you have three pipes. And the inner region corresponds to all three being at comparable distances from each other. When we want to take into account three-dimensional space, not planar, then the way we divide it is that we notice that at any point, three bodies define a plane. So then we can divide it into the motion of the plane divided by the three bodies and the motion within the plane, which is described by the geometry space. And then the motion of the plane is a little like rigid body. So we have now a vector of angular momentum, unlike in the planar case where angular momentum was a number. Now angular momentum is a vector, and we can use something similar to rigid body, only here the body is not rigid, but it is still rotating. So we treat separately the rotations of the plane, the motion, the orientation of the plane, and the motion of the 3 points within the plane, namely the geometry of the triangle. Okay, so now I think I can go back to the top.
Barak, can I ask a question here?
Yes.
So
please.
we can move inside the pipes as well, right? We're not constrained to the boundary of the pipe or
No, we are inside this surface
inside.
because
So what does the boundary
inside
correspond to?
inside the surface, the potential energy is smaller than on the surface, and outside the surface, the potential energy is higher. So it's a barrier. You cannot go outside of the surface, but you can be inside. And
so kind of the boundary of the pipes is the minimal kinetic energy.
yes, there it's zero kinetic energy, or the minimum that you need just to preserve angular momentum, which was, I think, already taken into account. By the way, the three lines here describe the points where two of the bodies are coincident. So, yeah. Okay.
Yes, thanks.
So now let's see, I want to go back to this talk. So I have to share. No, not here. Okay, but it's not shared. Just a minute. Okay, here. Okay, now I think you can see the screen. Oh. Okay, here is another thing that helps. How do we do Lagrangian mechanics in terms of non-coordinate velocities? So from GR, we're familiar with the fact that we can work either with a coordinate basis in space-time or with a non-coordinate basis. And then we have torsion coefficients. Something similar happens in mechanics. Suppose we want to work with velocities which are not qi dot, as we usually do, but some linear combinations of qi dot. Linear combinations which are not necessarily a derivative of some other function. So that means that there is a torsion. So when we take the differential of these one forms, we get something non-zero. So that means it's non-integrable. It cannot be written as the differential of some coordinate. And this turns out to be useful, at least for rigid body. And it was Poincaré who discovered this in 1901, and others rediscovered it later. One of the later ones was myself about a few years ago. And then the Euler-Lagrange equations gets another term. So you see here is the familiar term d by dt of the conjugate momentum, dl by dv instead of dl by dq dot. Here is the generalized force. You take a derivative of the Lagrangian in the direction of the EA is the vector field, which is conjugate to the one-form field beta. But there is an extra term that Poincaré understood, where here the torsion coefficients appear. Okay, so in this way, you can work in non-coordinate velocities. And in this way, you can make the rigid body, allow it a Lagrangian formulation and a Hamiltonian formulation. Usually you work in the body frame. And if you neglect this term, you would not reproduce the Euler equations of the rigid body. But if you include this term, then you exactly reproduce the Euler equations. Okay, so you can do, usually it's not taught this way, but you can do Lagrangian and Hamiltonian mechanics also for rigid body if you're aware of this story. All of this is described in an appendix to the paper. Okay, so we're done with the formulation. We have now this picture that instead of considering 3 points, so 9 degrees of freedom, after taking into account the Lagrangian and the, after taking into account the linear momentum and the angular momentum, we have this joint pipe, okay, which is not present here, and we have the rotation of the plane defined by the 3 points and the change of geometry within the plane. Okay, now let's look at the flux-based statistical theory. This is really, it helps, the previous part helps, but is not necessary. This part is actually independent of it. So here we'd like to discuss, I'll tell you here rather briefly what is the flux-based statistical theory and show you evidence for it. Okay? So the three-body problem is believed not to have a deterministic solution. This is known since Poincaré in 1890. I don't know if everybody here knows it, but I will assume it as known. Poincaré showed that there are no further conserved quantities other than the ones that we mentioned, the linear momentum, the angular momentum, and the energy. Therefore, there are fewer conserved quantities than degrees of freedom, more precisely, fewer that are in involution, or that their Poisson bracket is 0. So we have 9 degrees of freedom and 7 conserved quantities, out of which only 6 are in involution, I think. So, yes.
There's no Laplace-Runge length equivalent?
No, there is no Laplace-Runge length equivalent for the 3-body, unlike the 2-body. Yes, there we even have enhanced symmetry, but here there's nothing like it. And since we don't have conserved quantities, then in modern language, the problem is not integrable and we cannot solve it. And Poincaré even showed that certain perturbations can grow exponentially fast in time. And seen in another way, this is exponential sensitivity to initial conditions, because if you change the initial conditions only a little and then they grow exponentially in time, that means that you can never predict this system, because even if you measure the positions of the heavenly bodies to 1 kilometer, then within a few years, this 1 kilometer will turn into, I don't know, thousands and millions of kilometers. And even if you reduce it to millimeters, then it will just take a few more years. So we're all familiar with how fast the exponential grows. So there is no deterministic solution. We don't expect a closed form expression that will allow us to predict the motion of the 3-body system in the far future, maybe only for a few typical times, a few years. And if you look at the simulations, you see how random, like in behavior, they appear. If you want, I can show you one later. So the way people took Poincaré's discovery is to say, okay, there is no solution. But, well, in the 1960s, computers were applied to the 3-body problems, and people started looking at the statistics of what happens. Since it could not be predicted, maybe you can at least predict. You could find statistical patterns. So it's random-like motion, and it became apparent that the correct goal is that given initial conditions, I'm not sure what chaotic here means, given initial conditions, we want to seek a statistical solution, namely to ask what is the probability distribution for various outcomes. For instance, if we have 3 bodies moving, we're inside some star cluster, there's a binary, and the 3rd star is approaching. Then a 3-body motion will ensue, and this system is unstable to decay. And at some point, one of the 3 will be thrown out. It will escape. Which one of the 3 will escape? Well, there are probabilities. Which direction will it go? What velocity? What would be the parameters of the Keplerian motion? this is the question of a statistical solution. We cannot predict precisely what, but we can try to predict the statistical distribution. And then people started building statistical theories. Now, building these statistical theories is somewhat challenging. It's unlike the standard statistical theories that we learn in, I don't know, in our courses on statistical mechanics and physics, because this system ends ultimately in disintegration. It is unbounded. It's not inside any box. And regular and chaotic episodes may interchange. That means that while the three are close to each other, they move chaotically. But if they separate for some time, then they move regularly. The two binary orbit each other. One of them flies, the tertiary flies away. But if it's below the escape velocity, they will fall back. So all this motion is just a product of two Keplerian motions, the motion of the binary and the relative motion of the binary in the tertiary. So for a while, it could be regular, and then it falls back into chaotic, until finally there is an ejection, which is above the escape velocity, and then it is an escape. So all these...
Barak, can I ask a question? So is it the case that only the motion in the plane is chaotic and the motion of the plane itself is not chaotic, or are they both chaotic?
I would say that already the motion within the plane is chaotic. So if we divided the system into two things, two parts, two coupled parts, I should say, the rigid body or the rotating body, it's better to say, because it's not rigid. So the rotating body and the geometry space. The geometry space already is chaotic. So it's a three-dimensional motion in this joint pipe where we just have one conservation law, conservation of energy. So we have 3 degrees of freedom, one conservation law, it's not integrable, and it is chaotic. So this is the chaotic core. So in order to see chaos in the three-body problem, it suffices to consider the planar problem. Of course, if you go to the spatial problem, the three-dimensional, it is still chaotic, but the chaotic core is already in the planar case. Thank you for the question.
I see, but the kind of the dynamics of the plane itself will also be chaotic, induced by the core.
Yes.
Part.
So
okay.
yeah. So because they are coupled, I don't think in any sense I would say that it's chaotic also, the motion of the orientation of the plane defined by the three bodies. So we know that rigid body motion is integrable, rigid body motion. However, here it's non-rigid. The moments of inertia of this rotating body change as the geometry of the triangle changes. This is the coupling. The moments of inertia are dependent on the position in geometry space. So since that motion is chaotic, I think the whole motion is chaotic.
I see, thanks.
Now, statistical theories were suggested as early as 1976 by Monahan, Joe Monahan today from Australia. And it was based on statistical mechanics of Boltzmann and Gibbs, where we associate probability with phase-space volume. However, there were infinite space volume because it's unbounded. So then, in order to overcome this problem of infinite probabilities, this method introduced a kind of a cutoff, capital R, which was the strong interaction region. And it makes probabilities finite, and it allows somehow to separate regular from chaotic motion, but it is somewhat arbitrary. You get probability distributions which depend on this R, but this R is it's not decided from the data. It's kind of a free knob that is left to adjust in order to fit the results. So it's not a genuine theory, if you like, in this sense that it includes in it a free knob. Well, it is a theory, of course, but it's one that depends on an additional parameter. And the latest achievement was by Nick Stone from the Hebrew University and Nathan Lee in 2019. They found a formula in closed form for this distribution. And I heard about it reading Haaretz. There was a big headline, the three-body problem was solved. And I started reading. I knew about the three-body problem. I had thought about it even in analytical mechanics when I taught it. And then I saw that the person who solved it was from the Hebrew University, and I didn't know him because he had just arrived to the Hebrew University. And then I sat down with him, and then he showed me, look, we have this R, which is, he called it, Nick called it a fudge factor. He's an excellent physicist, of course. So let's call it a spurious parameter. And then I thought, just a minute, maybe we can deal with this cutoff. So there is a place for improvement, this free parameter R. And then just COVID broke out, if you remember. So this was December 2019 when I heard about it. And then COVID broke out in March, early March, and I got locked into this very home office that you see me now for a few months. And I developed a statistical theory. I re-examined the statistical theory and redeveloped it on a different basis. So I changed, the whole statistical theory was changed. And the final outcome was as follows. I want to skip to this equation and to give you some flavor to it. So here we have an equation for the decay rate. So that's the number of systems which disintegrate per unit time. So probability per unit time for disintegration. U are the outcome parameters. So as we mentioned, it's which one escapes, that's 1, 2, or 3, but mostly continuous parameters, directions, eccentricities of the binary. And then this D gamma in particular is the outcome distribution, because if you know what's the rate per unit time, then forgetting about time, it's just the different probabilities for all possible outcomes. So this is the thing that we're interested in. And this was written as a product of two functions. One of them is the flux, the asymptotic flux in phase space. And the other one is called the emissivity function. Now, the asymptotic flux, that's a quantity that we could determine in closed form precisely, because it has to do with a case where the two bodies, the binary is far away from the third. And here is the expression for it. I will not even explain much unless you ask me, but that has a closed form. And then the emissivity function, that remains unknown. But in some cases, the asymptotic flux is the dominant factor. So if you write the quantity of interest as a product of two functions, and one of them is dominant and you know it, then you make progress. Moreover, even in cases where epsilon, you want to take it into account, sorry, this emissivity, you want to take it into account, there is a simpler way to measure it that I will soon mention, rather than perform a full simulation. So it will be a reduction in the sense, it will be a reduction that we can write the gamma in terms of the emissivity function, where the emissivity functions requires less computation than gamma. And sometimes we can ignore it altogether. Let's see some results of numerical simulation. Oh, here is the definition of the emissivity. Suppose we have a binary and we shoot at it a tertiary, and we ask what is the probability for the chaotic absorption or capture given some random binary phase. So you randomize over the phase of the binary, and then you throw in the tertiary from always from the same direction, and you ask what is the chance that it will perform some chaotic motion. And this is called chaotic emissivity. We call it chaotic emissivity. So it's a number between 0 and 1. In particular, it is bounded, so it's already something nice that you can write it as a product of an unknown function, but it's a bounded function. Yes.
And does this epsilon depend on R as well, the cutoff?
No, R disappeared from the theory altogether. The strong interaction radius disappeared completely. So,
but then, how do you define?
We eliminated Shachar the phase space volume, and instead we consider the phase space flux. So we consider this joint pipe, and we can think of all the systems as some gas filling this pipe. Actually, we want to go to phase space where we see also the momentum, not only the positions. So then we have a gas that is filling this pipe, but and then it flies out, and the amount of gas that flies out, that's proportional to the decay rate. Yes, if you have, so you imagine that you have a closed container and it has a few punctures in it, a few holes, and then suppose you have a gas inside it, and you have one gas molecule that you're especially interested. You paint it red, and then you want to know which way will it go out of 3 holes, or if you have even 1 hole, what time would it take it to get out? Then you just look at the rate the gas is going out of the various holes, or even 1 hole in the container. And that will tell you, of course, because the red molecule is not different than all the gas molecules, it will give you the relative probability that it would live through either one of the holes, or how much time it would take it to live through either one of the holes. Okay, so the analog of the red system is the specific system that we're interested in. But now we're looking at all systems with prescribed conserved charges. That's all we care about, not the initial conditions that we have, just the conserved charges. And among this ensemble of systems with the same conserved charges, we want to look at the flux of phase space volume. And this flux of phase space volume now is, so we associate the decay rate with flux of phase space volume rather than probability with phase space volume. So instead of looking for probability, we look for decay rates. Instead of looking for phase space volumes, we look for fluxes. So the basis for the theory was changed. And now the fluxes are always finite. There is no issue of infinite. Even though this whole structure is infinite, the fluxes are finite. So infinities don't arise, at least not at this point. They arise in somewhere else that's related to the project with Yogesh, which I will not touch upon. But at this point, infinities don't arise, and we don't need a strong interaction radius anymore, and we don't have any spurious parameters. Okay. So that's why we call it the flux-based statistical theory. Yeah, let me go ahead, and if we want, I'll return to this point a little to say a few more things. But I want to show you the evidence. So right now, we will have 2 pieces of evidence that I want to highlight. We have by now 2 papers, but I want to highlight two points out of them. One is which one of the bodies escape. If the 3 bodies are of equal mass, then it doesn't matter what were the initial conditions, they will have equal probabilities to escape. This is just since the system is is really chaotic or really ergodic. This is what you expect. And indeed, this is what the simulations that we did show, that if the masses are equal, then the probabilities of escape are equal. What happens when the probabilities are not equal? Well, then we look at this quantity k, which we call the binary constant. So we have 3 possible binaries out of 3 bodies. For each binary, you can take the reduced mass and multiply it by the alpha squared. Alpha is the GMA MB, where MA and MB are the masses of the binary. So this is the potential strength. So potential strength squared times the reduced mass. We have 3 such Ks for the 3 possible binaries that can form, or the 3 possible escapes. And the formula is very simple. Under a certain condition, under a certain inequality that applies to the cases that we studied, to all the cases that we studied, then the probability, the unnormalized probability, simply goes like this K of S. S goes from 1 to 3. So K of S, if S is 1, that means that body 1 escapes, and then K is of the remaining binary, which are 2 and 3. You simply take Ks to the power 3/2. Okay, so this is a very extremely simple formula for the probability of escape for each one of the bodies. And now we can, here I have to go here, and let me show it here again. Okay, so here, what can we see? Sorry. Okay, so I want to show you the data that we have here. Yes. So this is a case of equal masses. Here, our theory predicts a third equal probability, and also other theories predict equal probabilities. And indeed, you measure equal probabilities, even though the initial conditions that we chose are not symmetrical. We have a binary and the third guy falling into the binary. But nevertheless, the probability of escape that is measured is equal. Okay, there's also an important cut that we apply here. Only systems that have decayed after a long enough motion, or after a chaotic motion, because some of the systems will undergo just regular motion, such as a flyby or an exchange, and then we don't have a chance of applying a statistical theory. So the statistical theory applies only after long enough chaotic motion. And in that case, we expect it to apply, and indeed it applies. Now, if you look at unequal masses, let's look at this case, 12, 15, 18, but all are very much the same. The measured probabilities are 62, 25, and 13. The simple formula that I showed you is 61, 26, and 13. You see how close it is, just amazingly close, 1% close. If you look at other theories that were suggested along the years, they give you the same tendency that the lighter object, the 12, has the higher probability of escaping. Yes, so if you have a 3-body system, then the lighter object has the higher escape probability. But if you do it quantitatively, the other theories, they give you the qualitative tendency, but they don't give you the quantitative numbers. And here you can look at any comparison of the K20 is the flux-based, and PS are the measured probabilities in simulation. and you can see how close they are. Here, look at these three numbers. They are really close at the 1% level. So this is a leap in accuracy, and the flux-based statistical theory of the three-body problem is the most precise statistical theory of the three-body problem to date. But we can do more than that. That's just a discrete variable, 1, 2, or 3. Which one escaped? We can also consider continuous variables. And this is what we did here. We measured the chaotic absorptivity in experiments. And that's a shorter measurement, because here you need to follow it only up to capture. You don't have to follow it up to disintegration. So in order to measure the outcome probabilities, you have to follow up to disintegration. While in order to measure the chaotic emissivity, it's enough to measure it only up to capture or non-capture. Okay, so in that sense, it's a shorter computation, reduced computation. So here we measure the emissivity, we multiply it by the flux factor, and that gives us a predicted distribution. And then we measure the distribution. And you compare these two. This is measured. This is what the theory predicts, given that you measured something else, the emissivity. And now it's it's a bivariate distribution. We measured the probability distribution over two continuous variables, which are the binary energy and the binary angular momentum. So the binary can go out. The remaining binary, these are the circular binaries. And you can see how close they are. In fact, we can even show it better how close they are. This is these are the contour maps. So one of them, it doesn't matter so much which one. One of them is the predicted, and the other one is the measured, the contour plots. You see how close they are. They're not only close to the eye, they're extremely close. Okay, great. So I think our time is over, and maybe even a little more than over. So sorry about this. So let me summarize, and then if I went too fast through something and there is a question, of course, I can answer. So I would say that the three-body problem has been cracked in the sense that we gave it new foundation, and for the statistical theory, we reduced the statistical solution, and it now remains to find the emissivity function. The emissivity function can be either measured, as we did, or we can find analytical models for that. That's an open issue. We achieved a leap in agreement with simulations. It's the most precise three-body problem in statistical theory to date. And I also showed you a new formulation, the dynamical reduction, which has various neat geometrical, physical aspects to it. Let's see, do I have another slide? Well, okay, just to show you that the first paper was published in April 2021, already almost 3 years ago, and then there was a lot of it was mentioned throughout the world. Here it's in the Scientific American website. Here it's in Bloomberg.com, 5 things to start the day. And there was also a Haaretz article. Okay, so I think with this, I hope the message was clear. In this talk, unlike other colloquium style talks, I didn't focus so much on the history and the motivation for studying the three-body problem, but rather I tried to really highlight a number of theoretical physics issues that were introduced during this work. And I thank you for your attention.
Thanks, Barak, for a very interesting talk. Any questions? Yeah, Ofik.
So did you use the new formulation from the first half of the talk for the problem in the second half of the talk?
No, not really. Well, first the reduction, the statistical theory was done before the dynamical reduction. So the chronological order was reversed to the order of the talk. The place where it can be used, well, we had several uses for the dynamical reduction paper. Well, first of all, it's nice to be able to think about the system instead of in 18 phase dimensions or 9 degrees of freedom. You reduce it to the essential part, which is 3 degrees of freedom in this geometry space. So this allows you to visualize. And in fact, you now remind me that I should say one more word, one more point. Where is it? Here, this point that moves inside of the joint pipe, you remember it? It moves under 2 kinds of forces. One is electric kind, which attracts it to the 3 lines of coincidence. So there is some kind of attraction to the 3 lines. In addition, there is a magnetic field. You see the blue arrows? That's a magnetic-like field, which actually comes from the Coriolis, because we're in a rotating system that we factored out the rotation of the triangle. So there is a magnetic-like force and an electric-like force. And this gives us a very physical picture, and that allows us to visualize more reasonably the system. There is one place where we actually use it, and that's for a project with Yogesh and Shubhajit that I didn't get to talk about, where we compute the total phase space volume, and that's in order to determine the decay rate. You see, so far we discussed the outcome probabilities, but how much time does it take to decay? All previous theories were not able to study that, the decay time. This theory is able to study the decay time, but it requires some more computations, and these computations were made feasible, were not completed. 1, were not completed, and 2, were made possible thanks to the new variables of the dynamical reduction. So the one-line answer to your question, which is a very valid question, is that the dynamical reduction should be essential for a theory of the decay time, which is so far uncompleted, but should be possible.
Okay, any more questions? I have one actually. So, I mean, of course, one can go to more bodies, like the n-body problem, and I'm just curious actually about the solar system. So, how? I mean, this is of course a hierarchical system, but still, are there estimates about I mean, how probable it is for things to become chaotic in the solar system? Is it at all? I mean, because it could have happened in the past, right? And
is the solar system chaotic, and in what sense?
I mean, now I guess it's quite far from chaotic, right? But
Well,
maybe it had a chaotic episodes in the past, or
well, it's a great question, partly by definition, because there has been a lot of work, not by myself, but by many others along the last 300 years on this question. So this is a question that already Newton worried about it. So it's known as the stability of the solar system. And the issue is as follows. Let me ask it just like you did, but in slightly different words. Before Newton, each planet moved on a track. It had a track and it moved around the sun. Newton threw out the tracks. Now everything hangs on a universal law of gravity. And now the motion of the Earth is in danger. It doesn't move on a track anymore, but any other planet, in particular the largest one, Jupiter, pulls it, exhibits a force on gravity on it. This force is small because the planets are much smaller than the sun, but over time, there's a danger that they would accumulate. And then maybe the Earth or any other system would fly out. And that would be an instability or a chaotic nature over a very long time. So at a time of order years, we can predict very well the motion because each planet moves separately around the sun, and we can predict the motion for a scale of years very well. But what happens of a scale of thousands or millions or billions of years? Can we still predict the motion? And here there's a very long story that will be part of a historical paper that I hope to complete at some point. And now, what can, well, I will say the bottom line, and if you want, and maybe a few more words. The bottom line is that today, according to simulations, we find that the solar system is unpredictable, or if you like, chaotic, for time in the range of around billion years. And even there, it's rather mild. And it appears first in the trajectory of Mercury, the closest one to the sun. Okay, so before that, so this is seen by changing by simulating the solar system. You change the position of Mercury by 1 millimeter, and you come back after several hundred millions or several billion years, and you find that it changed by a lot. Or at least that there is the Lyapunov exponent and it could have changed. So there's an issue of how you exactly define this instability. But this is the statement that people who study these simulations, there are a few researchers who are actively working and simulating this system. I'll just add that Newton was already worried about it, and he said that every once in a while, the system appears to require a what was the word that he used? A readjustment.
Reformation.
Reformation, thank you, Ofek, thank you. The system requires a reformation, and some Newton scholars describe it for a reason that I don't understand as a lifetime warranty from God, that after many years, after the orbit of the Earth will have drifted, God will return it to a safe orbit. Then Lagrange and Laplace found out that if you assume no resonances, or the so-called secular approximation, when you can average over long times, then the semi-major axis, the famous A of each planet, is conserved. So that means that under this secular approximation of very long times, the orbits can change, and they can become more or less eccentric, but the size of the orbit will not change. A will not change. And they call that the stability of the solar system. Of course, it's a very specific stability. It will not, for instance, it will not guarantee against a star flying out throughout the Milky Way and hitting the solar system and destroying it altogether, or all kinds of catastrophes, but it's a safety against accumulation of planetary perturbations from other planets. And later, Poincaré's work was interpreted as a different, stronger kind of stability of the solar system. But all of these stabilities are with some qualifications and limits. And finally, we have some positive results from simulations that I mentioned to you in the beginning. So it's a very interesting story going through Newton, Laplace and Lagrange, Poincaré, and others, still modern day researchers. One of them is Mogavero, who was supposed to arrive to our workshop in October, and he belongs to a whole French school of people who push this important work.
Great, thanks. So any other questions? Any last question, maybe? Okay, we're way over time. So let's thank Barak again. What?
Thank you all for coming.
Close the
Thank you.
recording.
Thank you, Shahab, for organizing.